Okay, great. So let's get started. So today we're going to continue our discussion of MRI. So before I begin, any questions from last lecture or about course logistics? Okay, so let's get started. Um, so we're going to review a little bit of what we did last time, and then we're going to move on to talking about relaxation, the block equation, review Fourier K-space, and then hopefully get to encoding with gradients, and hopefully by the end of today's lecture, the idea is that you'll have somewhat of a basic sense of how MRI, we actually create the images with MRI. So just to remind you, we're sort of walking through the sort of four main sort of tasks that an MRI system has to do. The first is polarization. Second is excitation, encoding, and integration. So hopefully by the end of this lecture, we'll have gotten through all of those as a first pass. And then the idea is we're going to keep revisiting these, probably sort of a multi-layered approach. So you'll sort of see these concepts multiple times. Um, so remember the job of the main magnet, which was on the quiz, was to to create polarization. So it's really so that we have this, when we apply a strong magnetic field, we have some equilibrium magnetization, and that's our signal to work with. Okay. So without that, there's really no net signal. If we had no magnetic field, then there'd be no net back signal. Um, and the other thing we talked about was precession, and I did remember to bring my bike wheel today, so get to do my annual bike wheel demonstration. So let's see if we can do that. All right, so I think people in Zoom can see me too. So this is going to be sort of a really useful analogy for a spin, right? Because it's got forces exerted on it, and it can also have angular momentum. Okay. So we're going to look at the case first where there's just forces exerted on it. So this is clearly the lowest energy state of this object, right? So this is where it wants to be. If I put it to here, I've got to put work into the system, right? So this is a higher energy state. Okay. This is analogous to a 90-degree flip angle. Okay. And if I put more work into the system, I could turn it all the way over here, right? And this would be analogous to 180-degree flip angle. Okay. So if there's no angular momentum, then it's just going to go back to its equilibrium state. And so that's sort of, if the spin had no momentum, that's where it would be. Um, but, and probably you've seen this, I can give it angular momentum. And so here, if I give it angular momentum, it's going to precess around. Okay, so this is exactly what the spin does. And you can imagine the magnetization is processing in this way. All right. And so that's sort of what these equations of motion are saying, is that the spin acts exactly like this bike wheel does. All right. So that's something you can keep in mind, and sort of a fun experiment. And then the angular frequency at which it processes is what's known as the Larmor frequency. All right, so use that on the pre-lecture quiz. So if you know B and you know gamma, then you can always calculate the Larmor frequency. So, and then in terms of hertz, it would be gamma over 2 pi times the B field. Okay. And gamma over 2 pi, it's roughly about 4257 hertz per Gauss. So for hydrogen proton. I think I put this slide in just because it is possible to do MRI just using the Earth's magnetic field. So even like sitting in this room, there is a magnetic field as you calculated, and you calculated that the frequency of the spins is about 4,000 hertz, right? Or 2,000 hertz, right? Um, so so right now, and these are two examples. This is one from Los Alamos that they've sort of set up so that the idea is if you had to go to sort of an area where there was some sort of chemical spill or some other sort of disaster, and you wanted to detect sort of different chemicals, you wouldn't have to lug out an expensive MRI machine. You could just go out and use the Earth's magnetic field and look at the spectrum. I think this was done by some students here. And if you're really ambitious, you can even build your own MRI scanner. There's a whole open source website to tell you how to build a scanner. Okay. That would be an amazing project, but obviously not required. Okay. All right, so then that's polarization. And so that's pretty much all we're going to say about polarization, which is basically we're creating this magnetization with large B0 field. And then remember, we have this sort of large B naught field, right? And this is going to be the Z-axis, let's say. And so the spins will process around this field, right? And then we come along with a really, really tiny field here, right? And if this was the only field, then the spins would process around this field, okay? But since this field is much larger, then the only way we can get spins to process to follow this field is this field that we apply, this B1 field, has to be at the Larmor frequency, all right? It has to be at the resonant frequency. And so that's one of the things we talked about, all right? And one way to think about that is if I go from the laboratory frame to the rotating frame, right? In the laboratory frame, the spin is processing. Okay, so yes.
So if the B0 field like polarizes it towards a certain direction, what does the B1 field do?
The B1 field is what takes the magnet. So the B0 field makes it so the magnetization has a preferred orientation. And the B1 field is such that we tip the magnetization away from the B0 field so that we can more easily detect this precession. Okay, it's sort of what we talked about last time. Like am I rotating this or am I not rotating it? You can't really tell, right? But if I do this, you can easily tell if I'm rotating it.
Okay.
So that's sort of the analogy of, I mean, obviously this is just sort of a way to think about why that makes sense. All right.
So in order to do, like we do that basically to pick up on the signal, right?
Yeah, to create a signal that we can detect. Okay, because basically we're going to detect the signal with a coil out here, which could just be a loop of wire. And so we want something that creates a time varying magnetic field here. Okay. And so we need to get the precession in a place where the magnetization is going to create this time varying field, right? So the idea is that if I have precession, if I see a spin processing, then I can infer that there's a B0 field there, right? But remember, that's in the laboratory frame, right? In the rotating frame, the spin's just like that, right? The spin's not processing because I'm going along with the spin. So if a spin is not processing, then I could infer that there's no B0 field, right? So in the rotating frame, the B0 field, if you're on resonance, essentially disappears. Okay. So that means the only field you see is this B1 field, which since it's going at the same rate as you are, it stays static. And so now you can just look at precession around this little field. Okay. And so that's the way to think about why going from the laboratory frame to the rotating frame sort of simplifies things. So we typically, unless you're doing something really, really advanced, you're always in the laboratory frame. Okay. And so, but this one here is still in the you always want to be in the rotating frame, but this one here is still in the laboratory frame just to get you the basic concepts to remind you that all the magnetization is processing, but we really just follow the net magnetization and see what it's doing. All right, so this is basically getting it away from its equilibrium state. We talked about a little bit about how important it is to be on resonance. So if the blue arrow is the B1 field and the red is the magnetization, and if we're on resonance, that's what allows us to get that magnetization off the equilibrium state. And if we are not on resonance, if we're not applying it on resonance, then the B0, the magnetization stays very close to the B naught field, right? And that's why the importance of the rotating frame of reference. And so this is a nice picture showing that, for example, in the laboratory frame, this magnetization has a relatively complicated evolution that we would have to keep track of. But in the rotating frame of reference, it's just a simple rotation. And if you want to sort of remember the rotation, it's always the left-hand rule. You put your thumb in line with the magnetization, the applied B field, and the rotation will be where your fingers curve. So the B1 field's that way, so I know the magnetization, it's going to go like that in the picture. All right. And so in the rotating frame of reference, it's doing exactly that. It's tipping down this way. So that is sort of the job of the RF excitation pulse. And we talked about the flip angle, which had a relatively simple calculation. We did an example of that in class as well. So just to remind you what we did. So now so that's review. So are there any questions about that before we start on some new material? Yes.
What was the what's the concept behind the flip angle?
What is the flip angle? Or the flip angle is essentially what's the angle that you flip the magnetization away from equilibrium. Okay.
Oh, okay.
So you can imagine that. And so for now, we're just going to assume that you flipped it to 90 degrees is the simplest thing. Okay. But later on, we're going to see how you can choose sort of different flip angles.
And then this is the angle caused by E1, right?
Yes,
Okay.
that's right. Yeah. Yes, question.
Laboratory frame.
Sure. Yeah. The laboratory frame is essentially like like you're outside, like let's say we have an object in a magnet and we polarize it and we excite it. Then if we could look at the magnetization, we're sitting out here, that magnetization looks like it's moving around, right? And so then therefore, it's like if this is a magnet and it's changing like this, then when I'm looking over here in the laboratory frame, I will see a time varying magnetic field. So that is actually what we are in the real world. We're in the laboratory frame, right? So we can do the measurement, right? But to do the math, it's useful to think, well, what if I was in the same frame, to keep things simple, as the spin, right? Then yeah, it's just sort of saying which frame you're in. Yeah. So that's used a lot in physics because sometimes things are really messy in one frame. So you want to go to a frame where they're simpler, right? Otherwise, it's the same physics, but it's just how much math you want to do. Okay. And generally, we don't want to do that much math. Okay. Yes, question.
If magnetic magnetic moment is perfectly aligned with the primary magnetic field, there will be the net torque will be zero, right? And so it won't start any spiral spiraling motion, right? First, if the magnetic moment is perfectly aligned with magnetic.
Yeah, that's a sort of subtle, interesting point. So the idea is, even though we think about a magnetic moment, it's actually, I mean, we can't really get into all the quantum mechanics, but you have to still imagine that there are spins at all these orientations, which is represented by all these little arrows here, right? So all those spins are still processing, but the net magnetization is not, right? So that's one way to look at it. But the thing is that, with quantum mechanics, so those of you know about it, you don't really know what the state is until you measure it, right? And so you just have to assume that spins can be in all these different probabilities, and it's like all the spins are spinning around, but just the net is there. Yeah. So you could imagine it's sort of spinning around its own axis, but these are all classical analogies for, for things that we don't really understand. Okay. All right. Anything? Yeah, question.
This kind of direction, like ultimately going like this.
So this is this the magnetization you mean? Yeah, so the magnetization in the laboratory frame, it would spiral down because it's being tipped away and it's as if you, for example, it's this analogy here. Oh, yeah. This analogy here, like let's say you're standing here, right? And someone is pulling you very slowly as you're spinning around. So you would sort of, in the laboratory frame, you would be like, this is you standing up, you'd be slowly pulled off, but you're spinning around at the same time.
Yeah, but like the rate of pulling away would differ if I'm standing here versus I'm standing here.
Yeah, and they're running around with the frame. They have to spin around at the same rate that the merry-go-round is going.
The video looks like everything is moving at the same rate because within the pixels.
Sorry, can you say that again?
So the one vector which is here and here would accelerate at a different rate, right?
So the way to think about it is, if this is the magnetization, and then my thumb is the B1 field. So I have to apply this B1 field at the same rate as this spin wants to turn. Yeah, so that's this picture here. If you look at this movie here, the cyan and the red are going at the same rate. So they're always in sync. Okay. If they're not in sync, then see the cyan is going much faster than the red. So then they're not in sync. So initially we want to be on resonance. Okay, good. Okay, so I'm just going to work through some math just to get to sort of set up some notation, but it'll be fairly straightforward. So basically, we're just going to remind you that this is the equation of motion. So it's m cross gamma b, which usually in life, unless you're like an E&M person, you don't do cross products or that much. So you might have to remember that you can represent it as the determinant of this matrix, which is given by this. So just this is sort of the expression. Just breaking it down into the components of M and the components of B of these two vectors. So where this is the magnetization and this is the B field. And then we can write this in matrix form as follows, where we have the change in each component of the magnetization is proportional to the magnetization that's there times these components, all right? And for now, so we're looking at, we've got the BX, BY, and BZ components. And so to understand the solution, we are going to use a lot of phasors in MRI, and really the underlying physics and math is just, if you think in terms of phasors, then your life is just much easier, okay? So just to remind you, everything is e to the j theta. Okay, you just want to think of it. We typically draw it as a vector, a unit vector. And this is theta equals 0, theta equals minus pi over 2, theta equals pi, theta equals pi over 2. All right, so theta is just this angle. And so basically everything is just what is the angle of the phasor. All right. And so it turns out that if we only have, we're going to look at the simplest case where we only have a B0 field. Okay, and we're going to see how this matrix multiplication, the solution to it, represents precession. Okay, so if you look at this equation, first of all, you notice that dmz dt equals 0, right? So that just means mz is some constant, right? So it's not the m sub z, the longitudinal component. So if this is my magnetization, the m sub z is this longitudinal component, okay? So that just means that this component is not going to change. Therefore, we expect a solution, a solution like this is consistent with mz being constant, right? So what's the more interesting thing is we want to look at this one here, which is dmx dt equals b naught times m sub y. dmy dt will turn out to be minus gamma b naught times m sub x, right? If you do the matrix multiplication. So here's probably the most critical part. We're going to define our magnetization, and this is going to be the transverse magnetization. Okay, so transverse just means what we define as transverse is basically the XY plane is our transverse plane. Okay, so this is the longitudinal plane, the one that's aligned with Z, and the transverse plane is the XY plane. All right, so that's just the notation we'll use. And so we're just saying that we can define this complex vector M as just a vector where we have the MX component on the x-axis and J times the MY component on the y-axis, right? And so this is just sort of the complex number notation or representation you probably learned in high school, all right? So the nice thing is then we can write dm dt equals minus j gamma b naught times m. And this is a first order differential equation, and you all know the solution is just an exponential, right? So you can guess the solution is an exponential and then solve for, what the exponent would be. And it turns out the solution is just m of t equals the initial condition times e to the minus j omega naught t, okay? Where omega naught is just equal to gamma b naught, all right? So that's the Larmor frequency. Okay, so the question is, which way does this rotate with time? So there's two options. It can either rotate clockwise or anti-clockwise. Okay, so let's say time is greater than 0. So which way is this going to go? Is it going to go clockwise or anti-clockwise? Sorry? Clockwise, right. Because the angle is getting more negative, right? So because we said negative angles are this way, so So basically, as you're doing your homework problems, just realize that that's the negative angle is this way. Okay. So that means that's also consistent with our left-hand rule, right? Because we said if there's a B field, we use the left-hand rule to decide which is the orientation of precession. And so this, if this is the transverse plane, this would be a negative angle. Okay. So it's all consistent.
Why the left hand rule on the right?
Left-hand rule. I'm just using, sorry, what was your question?
Why left and not right? Normally it's right, right?
Well, it just depends on what you're looking at. There are left and right-hand rules in physics. So it's the left-hand rule for this one. Yeah. Okay. Okay, so now we're going to start talking about, we talked about excitation. We're going to get into, and that's sort of the transmit side. So you can think of, we come in with a coil, okay, and the same RF coil is going to be used for both transmit and receive. So this coil applies some energy, an RF pulse, okay, and that tips the magnetization. So we apply the RF pulse and it tips the magnetization, right? And this magnetization wants to go back to here, right? So we now need to consider how does it go back to the original state? And that process is called relaxation. And the signal you get as it's processing around, this is the MR signal you'd get, because imagine I have a coil here and it's measuring this, but this is not going to happen forever, right? At some point, it's going to go back to here, right? So I tip it, it processes, and then it stops. Okay, goes back to equilibrium. So the signal we measure is going to look like a decaying sinusoid, right? And that's what's called the free induction decay. That's the most basic signal you have in MR. And so this is what it looks like. It starts off here. Let's say we applied a 90-degree flip angle. So we've taken all the magnetization and put it into the transverse plane, and it's going to spiral down to here. And this is what the signal looks like. All right. Yes.
That's because we stopped applying the B1?
Yes, that's a great question. So for most MR experiments, you apply a B1 pulse, and typically it's a pulse. Now there are, that's for most experiments. There are other experiments where you can keep it on for a long time. But for now, just assume we've applied a pulse, like the pulse that we looked at last class. You design the parameters, and there'll be some homework problems where you'll be looking at RF pulses, and then we stop, and then we watch what happens. Okay. Yes.
Polarization and excitation only affect hydrogen electron or other
Yeah, so that's a great question. So the question is, am I affecting other protons? So there's two things. One is there's like, for example, the hydrogen proton, its resonance frequency actually depends on its local environment. Okay, so not all hydrogen protons have the same resonance frequency. So for example, hydrogen in fat will have a different resonance frequency than hydrogen in sort of muscle and brain. And so the idea is, if you're on resonance for water in like brain, then that will preferentially tip the magnetization in the muscle and not in the fat. But depending on the bandwidth of your pulse, it might tip some of the fat as well. So we'll get a little into that when we talk about slice selection. That'll be quite a few lectures down the way. But for now, yes, just assume if you had an ideal case, you're only tipping the spins that you want to. In reality, there's a lot of complications. Yeah. Okay. Okay, so now we're going to talk about relaxation. To sort of, and what we're going to do is we're going to tell you what relaxation is, but we're not going to tell you really how it works. We'll come back to that later, just so you have an overview of where we're going. Yes, question.
So on the right hand side, the MR signal is so is described in an idealized scenario?
You mean this one here?
Yeah.
Yeah, so the coil stays here, and basically, as this magnetization is decaying, it's as if I had a magnet that was spinning around and the strength of the magnet was shrinking, right? So that would mean that if I were to, from Maxwell's equations, the dB dt is also getting smaller. So this frequency here is a Larmor frequency. So basically, the signal you measure is at the alarm frequency, and then it's just decaying away because the source magnetization is decaying away.
In the real life scenario, is the coil always gonna be at a constant rate, or is it always gonna be constant rate?
You mean is the precession at the
Yeah.
constant rate? Yes, yes, because that's determined by the physics of the situation. The only time it would be different is if you had something that changed the local magnetic field, which you could imagine doing that, and there could be experiments where you might even try to do that. Yeah, so I think we'll get to that. I'm not sure we have this slide in here, but spins are really nice because they do exactly what you tell them to do. Like whatever field is there, they will process at that rate, right? But the problem is you don't always know what field is there. Okay. If you knew, then if you knew everything about the sample, you would know exactly what the signal was. But typically, there's a lot of stuff we don't know. Okay. Yes.
Is signal amplitude MXY?
Yeah, so the way to think about it is right. So the signal that we care about is the transverse component because the longitudinal component doesn't create a time-varying magnetic field from a coil's point of view, right? Yeah. Okay. Okay, so we are going to look at now the relaxation. So basically, we've tipped the magnetization away and we need to see what happens to it. And so now we really need to break it into, and it turns out there's really two relaxation things happening simultaneously, and they're related, but they're not the same, okay? So today we're just going to give you sort of a very high-level overview. We'll come back in a few weeks and give you like the detailed physiology and physics behind it, all right? So we have to break it into a longitudinal component, the Z component, and the transverse, the XY components, all right? And so there's two time constants. One is T1, which is a spin lattice time constant. And this is the return to equilibrium of the M sub Z. So the way to think about this is, if I have here, M sub Z is, let's say, at full magnetization. When I tip it here, it's gone to 0, right? But it wants to return back to this, okay? So that's the T1 relaxation. The T2 is I've created this, I've here, I have no MXY component, right? I create it with the excitation. This is going to die away, okay? These two things, this growing and this dying away, are related, but not the same. And they actually have different time constants. So it's not as if one shrinks and one grows at the same time. This will tend to shrink faster than this grows back in most tissues, okay? So, but they're both the return to equilibrium. The equilibrium state is this, okay? Where we have some M0 component, which is like the initial value of the M of the magnetization, and we have a 0 transverse component. So the nice thing is that after all that, to first order, for most applications, then these are just governed by first order differential equations, right? So this is just saying that dmz dt is going to be driven by the difference between the current mz and M0, which is its equilibrium value, with some time constant T1, okay? So you know, so what that means is, for example, after 90-degree pulse, I would start off at Z equal to 0, right? And this is just going to grow back exponentially to M sub 0, right? This is some M sub 0. All right, and the physics behind that we'll get into later, but for now, you just assume that this is true, which it is. It's basically, if you go and measure magnetization, and if you can look at the longitudinal component, it has this characteristic. So why does that matter? Because basically different tissues have different T1s, right? And so this is what allows contrast. If they all had the same T1, then at least we wouldn't be able to use different T1 sensitive sequences to look at different contrasts. So today we'll just give you a sort of an overview of that, and then later on we'll go into how do you actually tweak the MRI to give you different contrast. Question?
Saying the hydrogen in those tissues have different contrast?
Yeah, they have different T1s. Yeah, they have different time constants. Yeah, so, and it's field dependent. So here we plotted the magnetic field strength. So this is the T1 here, and this is the field strength. So at like 1.5 Tesla, you see fat has a time constant of about 250 milliseconds, and muscle is up to almost close to a second.
But it's only
Yes, this is for the hydrogen. Yes, that's right. Yeah.
So this T1 value is referring to like how much time it'll take for it to go back to that like longitudinal like relaxation state or.
It's referring to the M sub Z component growing back. So yeah, it's more like, it's not like the magnetization. The magnetization, like we can think of the magnetization flipping back. On the way back, it doesn't go like this. Okay, it sort of, we'll show some pictures. It shrinks and grows. It's sort of like, like that.
Oh, it's okay.
Yeah,
Okay.
yeah. You'll see some picture of that in a few minutes. Okay. The other one we have to talk to is transverse relaxation. So this one has a even simpler first order equation, which just means this is an exponential decay. So if I start some magnetization here, it just decays exponentially with a time constant of T2. All right. And then the fact is you can show, which you will be doing on your homework, that T2 must be less than T1 in order for the magnetization never to get bigger than its equilibrium state. All right. And that's because physically they share some of the same mechanisms, which we'll talk about later, but they're not exactly the same. Okay, so there's some overlap in what causes them, but they have each sensitive to different qualities, which allows us to use both T1 and T2 to sort of differentiate different tissues or different disease states. So this is sort of the free induction decay that you saw. So this just has this envelope here is what's decaying with e to the minus t over t2. Question? Oh, yeah. We will get to that later. Yeah. Yeah. Okay. So T2 values typically are shorter than T1, as basically we just said that T2 is less than T1, and in many cases it's much less than T1 in general for lots of biological tissue. So you can sort of see here, it's on the order of like 50 to 100 milliseconds, whereas T1 in biological tissue at 3 Tesla is around 1 second. Okay. The only sort of exception to the rule is things with a lot of fluids. Like fluids, so CSF here stands for cerebral spinal fluid. That's the fluid that bathes your brain. That has a very long T2, which we'll get into why that is. So it turns out that fluids have both very long T1s and T2s. Pretty much everything else, has longer T1 than T2. So it turns out that the main mechanism behind the T2 decay is the event. Imagine we said when we look at any given sort of chunk of tissue or a voxel, so the term voxel just refers to, everyone knows what a pixel is, right? So voxel is just a 3D pixel, right? It's just a little volume, all right? So in any voxel, we're not looking at just any one spin, we're looking at lots of spins, right? And we're taking the sum of those. So the idea is initially they're all spinning at the same rate, right? They're all sort of in sync, right? But it turns out because of random interactions, they sort of get out of sync, and that getting out of sync that causes that transverse magnetization to decay. All right. Question? Yes, that's right. So the T1 and T2 will be different at field strengths. Yeah. So for example, T2 would be much shorter. Will tend to be a little slightly shorter, but T1 tends to be more sensitive. Yeah. Okay. And a lot of that is also determined by oftentimes, which we'll get to is, so right now we're talking about T1 and T2. These are sort of intrinsic physical properties of tissue, but there's one other thing we won't talk about today is called T2 star, which is like the effective relaxation rate. And that's affected by other things as well. So essentially, we're going to go sort of high level and then we'll sort of get deeper and deeper. Okay. Okay, so I'm just gonna, I know this comes out of nowhere. We're just gonna walk you through it. We're not gonna ask you to derive it, just to show that this is the governing equation of MRI. And it's named after Felix Bloch, who was one of the discoverers of nuclear magnetic resonance, won the Nobel Prize with Edward Purcell, I think sometime in I forget when, 40s or 50s. So this equation is named after him, okay? So just to walk you through it, the components are, it's always talking about the change with time of the magnetization. So there's the precession, which we talked about, okay? And then there's the relaxation, the T2 decay, and then there's the T1 recovery or relaxation. Okay, so that's all that's saying. In matrix format, all it means is that previously we had these terms here. Okay, now we for the because these are sort of decaying terms, they come along the diagonal, and plus for the T1 we add this additional term saying that's what we're going back to. Okay, these are 0 because we're going back to 0 for those, but this is headed towards this. Okay, towards M naught. Okay, so then what we can say is that the general solution for the M sub z is just, it's going to go to, it wants to go back to here, M0, and it's going to do that with this correction term that decays away with the exponential time constant of T1, okay? So saturation recovery just refers to, if I applied a 90-degree flip angle, so at time equals 0, M sub z is equal to 0. Okay, and so that's just this recovery. All right. The other thing that's really sort of just starting our sort of discussion of why would you pick some other flip angle? Let's say I picked a flip angle of 180 degrees, right? Then I would start off at minus M0 because I would have flipped the magnetization all the way down here, right? And now the recovery is going to look like that. Okay. So why might that be a useful thing to do? Why would you ever want to do something like that? Like what's special about that curve?
0.
It's crossing 0 at some point, right? So what, could you imagine using that somehow? So basically it means that if I have a tissue with a certain T1 and I acquire it at this point, its signal is 0, right? So I have a way of erasing tissue I don't want to look at. So for example, let's say there's a lot of fluid. Typically, for example, in maybe there's a lot of fluid around my tumor, right? And my signal is being dominated by all that fluid. So I want to erase I want to get rid of the magnetization from that fluid. So then I can sort of more clearly see what else is there. All right. So this is inversion recovery. It's a very standard approach for getting basically erasing tissues. And we'll look at some examples of that later. Okay, so at the end of the day, what happens is we have this complex magnetization, which has mx plus my component. And when we plug it into the equation, now before we have this minus j omega naught, now we just have this 1 over T2 term, okay? So we solve this first order differential equation. Our solution is essentially what we had before. This is just precession, right? And then this is the T2 decay. Okay, so if you think about magnetization in the MXY plane, this is sort of saying it's going to precess in the clockwise. Yes, question?
Yeah, so when you say precession, that's just like the equation that's representing the movement of that field, right?
Yeah, it's just basically the Larmor frequency. Yeah, yeah. So right. So yes. So basically, sometimes, you know, to sort of give you sort of the so we are in the laboratory frame here still, okay, because we are looking at the precession. But once we understand what the laboratory frame is, at some point we're going to forget about the laboratory frame. Okay. So just in the laboratory frame, it's easier to show there is precession and there is decay. And so it's going like that. And so this is going to show you, this is a nice movie from Brian Hargraves at Stanford, which shows you a movie that's going to show you this spiraling down, and you're going to sort of see the MXY component decay, and you're going to see this M sub Z component recovers, but a little more slowly. Okay. So MXY has basically gone to 0 at this point, but M sub Z is still recovering. Okay, and that just reflects the fact that the T1 is longer than the T2. Okay, so that's why these are two related, but not exact, but somewhat independent relaxation rates. And so what it looks like here is if I were to draw all the magnetization, the MXY is sort of decaying away. The M sub Z is growing back, but much slower. And so we sort of spiral down as we're growing up a little bit. And then by the time MXY has decayed, I still have M sub Z recovery to do. Okay, so that's what the magnetization will look like in the laboratory frame. And so what we'll do later in the course is we're going to get back and look at, so these are three different tissues, CSF, gray and white. You see they have different T1s and different T2s. And they also have something different that we haven't talked about yet, which is proton density, which is like how much water there is per unit area, okay, or per unit weight, okay? So that's also going to play into to what the images look like. And it turns out that once we sort of figure out how to make images with MR, we're going to come back and say, okay, now that we know how to make images, how do we make images with contrast? Okay. And so it turns out that these are all the same subject, right? All we've done is change the timing parameters in our pulse sequence and some of the flip angles to get these different contrasts. Okay. So in one case, these are the ventricles where you have a lot of cerebrospinal fluid. In this case, it's quite dark, right? And in this case, it's super bright, right? So just by changing our parameters, we can sort of accentuate different aspects of the tissue. So that's what we'll get into when we talk about contrast. Okay, so any questions on that? So we've done excitation, a little bit of relaxation. So now we're going to move on to encoding, which is where the magic happens in terms of this is what is we need to, encoding and integration are what we need to understand how do we actually make an image? How does MRI actually work? Question.
Does the norm of the magnetization change while it goes back to the original direction?
Does the norm?
Yeah, does the length of the same?
Let's see, does the norm change? Well, it always has to be less than M sub M naught, right? I think it, yeah, I think it can, because if you had a very short T2 tissue, yeah, you can imagine a very short T2 tissue where that disappears and then you're still waiting for the M sub Z to grow back. Yeah. Yeah, I mean, let's think. Yeah, because the dephasing, right? Because it's sort of like, yeah, because there's nothing special about the equilibrium magnetization, right? In an object, because essentially that's just a sum of all these individual spins, right? So even if I can somehow, if they're in, it's only the fact that they're in sync that creates this net magnetization. So anything that gets them out of sync will destroy that. Yeah. Until the longitudinal stuff gets it back to where you don't, so if they're in the equilibrium state, you assume everything is out of sync in the transverse plane. So all you're left with is that. So yeah, you could have a state where things are out of sync before this goes back. Yep. Good question. Okay. Anything else? Okay. So yeah. So now we're gonna cover. So we've covered the main magnet, we've covered the RF, and we're going to look at the gradients now. And so we're going to spend quite a few lectures now on talking about how do you make an image and how do you actually design sort of imaging for MRI. And then once we understand how we make the images, then we'll come back and look at what are the applications that you can do now that you understand how to make images. Okay. So just a reminder that there are 3 gradient coils for most standard magnets. There are other interesting designs, but the standard design is an X coil, a Y coil, and a Z coil. They tend to have fairly interesting wire patterns to generate the fields. So the key is that, as a reminder, spins process at the lower frequency. So in a constant field where B sub Z equals B naught, then they'll all spin at the same frequency. Okay. And here I'm saying ignore chemical shift. This is getting to your question about, certain spins will process at different rates. Like if you're in fat, you'll process differently than if you're in a muscle. But for now, we're going to ignore that. All right. So with the gradient coils are used to add spatial variation to B sub Z. So B sub Z now has X, Y, and Z dependence. So it has the main field plus this delta field. And this is what we use to create this will allow us to do the imaging. Okay. And since we can do that, that means that spins at different physical locations, we can now make them process at different frequencies. Question?
Is that delta B, is that the B1 field or?
No, this is the field that's created by the gradients. Yeah, this is due to the gradients. So the RF coils for the B1. Now we're adding our third coil, right? And this creates linear gradients in the field, which we'll show. Okay. So yeah, we'll show it right here. Okay. So what it means is that a gradient looks like this, right? At the isocenter, and remember, this is a special place. The isocenter is the center of our magnet where there's no added gradients from our system, ideally, okay? So there you can always assume the spins are always at gamma times B naught, all right? If I have a gradient in the x direction, remember, the gradient is defined such that the delta field it adds in the z direction is gx times x. So if I have a positive gradient, then it's going to look like this. So gamma B naught plus gamma gxx, all these spins out here experience a slightly higher field, okay? And therefore, they're going to process a little faster, okay? These spins here, they're in an area where there's a negative contribution to the gradient, and so they're going to spin a little slower. And basically, that's the whole key that we need to do. We need to get these spins out of sync, so then we can start applying, making it look like a Fourier transform. Okay, so this is a movie showing that. So basically, I think let's assume this is the x direction. So you can sort of see here, and now we are in the rotating frame. Okay, so the spins at the isocenter here, we assume if we're in the rotating frame, remember, something's processing. If we're in the laboratory frame, in the rotating frame, it just stays still. Okay, so at the isocenter, notice here, these stay still, but these spins here are spinning a little faster, and these spins here are spinning a little faster, and then these are going in the opposite direction, okay? Because if I'm spinning fast, if I'm at a faster precession frequency, you know, I'll appear to this, like let's say this spin here is my reference, right? And I'm going faster than him, then I will appear as if I'm to have a net clockwise rotation, right? Conversely, if this is the middle spin and this spin is going slower, then with respect to this spin, it's sort of going the opposite direction, right? It's lagging behind. So it looks like it's going counterclockwise. Okay, so everything is this relative rotational motion. And so you can sort of, you look at that, the orientation of these rotation is different here. So in this case, there's a gradient going this way, right? That's the orientation of the gradient, right? Because I'm causing variations in that direction in the rotation, right? If I look at this one here, everything is okay this way. So all the differences are happening in this axis. So here I would have applied a gradient in the y direction. Okay, such that, so here's a question. Which are spinning faster? Are these spinning faster, the ones below, or the ones above spinning faster? Like where is the gradient stronger here, or is it stronger here? Like where am I adding more field? Below or above? Below, right? Yeah, because these are sort of going clockwise with respect to these guys, so they must be processing faster. And these are going counterclockwise, so they're sort of relatively going slower. Okay. Here, notice that the gradient, the line where there's no sort of relative motion is this diagonal. So this means I've applied a gradient in both the x direction and the y direction, right? So the net gradient is the sum of that. So I've applied a gradient in that direction. So if you notice here, these are spinning faster, so they're in a stronger field. These are spinning slower, so they're in a negative field. And then as I go out in this direction, these are spinning much faster than these are spinning, right? So that's what the gradients look like. So that's the basics behind what's going on in an MRI system. We're just making spins go at different frequencies. Okay, and then we're looking at that at different points in time. Okay, so let's look at an example problem. This used to be on the homework, but now it's just, we'll do it in class. So here we say that we're in a gradient, right? So the B sub z is said, it looks like one, it has some overall B naught, right? But we're just going to look at the delta BZ term. So the delta BZ term is just 0.5 times Z, and we're assuming this is in the Z direction. Okay, so we've applied a gradient in the z direction, and so the delta B field generated by that gradient is just this term here. All right. So at time t equals 0, all the spins are in phase. Okay, and that's going to be our typical assumption for MR. Ideal case is when we apply that RF excitation pulse, all the spins are in phase. And now we apply this gradient, and now all the spins are going to get out of phase with each other. And the question is, let's say I'm at z equals 0 centimeters, and I'm also at another location. I'm looking at another location z equals 1 centimeter. Okay. So the question is, they are originally in phase, but they're going to get out of phase. How much time do I have to wait till they're back in phase again? Okay. So we know that then the rotation angle, the relative rotation angle has to be, we're looking for some rotation angle of 2 pi, right? How long does it take to go 2 pi radians or one complete cycle? Okay. So we know that the delta B, so we know that the relative frequency shift, so the delta frequency shift is going to be gamma times the delta B. Okay. That's the increase in frequency. It's going to be, so that's going to be equal to gamma. Oh, so gamma over 2 pi, sorry. Okay. Times 0.5 Z. Okay. So we have, this is going to be 42.57 megahertz per Tesla. And at 0.5, and assuming this is all in Tesla, right? We have 0.5 times 1 Tesla centimeters. Okay. So what? Oh, times Z. Yeah, I think the way they've written it, we will ignore this unit here. Okay. So I think it's implicit that the gradient has, the gradient's going to have a Tesla per centimeter. So it's going to sort of divide out. Okay. So that equals, let's say that's roughly 21 megahertz difference in frequency, which is a lot. So this is a made up problem. That means that this spin here is going, as respect to the spin at the isocenter, its relative frequency is 21 megahertz. Okay. So therefore, one period is just 1 over that delta F, right? So the period of that is equal to 1 over delta F. Okay. So if you do that math, which I think we'll do on the next page, yeah, one cycle is just that. So it takes 1 over delta F just takes 0.047 microseconds. Okay. And then if we look at other points, right? So for example, here, we looked at 1 centimeter, right? But we could also look at half a centimeter, okay? Or 0.25 centimeters, or 0.75 centimeters. And we could ask, how long does it take those spins to get back into phase? Okay. So for example, so we could either do the math, or we could just sort of think about what the answer should be. Okay. So it took this spin 0.047 microseconds to do a full rotation, right? Now this spin here is half the distance away. So its delta B is going to be half. So its delta F is going to be half, right? So therefore its period must be double the period. So it would take twice as long because it's going twice as slow, right? To get back into phase. Okay. So that's sort of what the gradients are doing. They're just basically making it so that the spins are at different frequencies. So it's going to take longer for spins at lower gradients to sort of make the same angle as the spin at a higher gradient. Okay. Sorry, question?
Saying they're back at phase, is it right that they're only at that point in time on the same position, but then continue spinning on a different?
Yeah, yeah, exactly. So for example, what I mean by in phase is when they're all in phase, they all start off in phase. Okay. And then they slowly get out of phase, right? Right. And so at that point, you know, this one at say some later point in time, this will get back in phase. And at that point, this one will also be back in phase. Okay, because this was just had double the period of the other one. So it's just getting out of phase that we're going to be looking at next. All right, question.
That change of frequency is the frequency of one spin or?
Well, it's basically, yeah, I mean, it's basically we apply a gradient in space. So we don't really think about one spin, but so all the magnetization at that location will have that frequency. Rough, it's basically the average field at that location over basically in imaging, you look over all the spins in a certain volume or voxel. So it's basically what's the average delta B in this voxel will be the rate. Yeah.
The rate, but I don't understand what rate are we talking about?
So basically, if you have an object here, so let's say I have different voxels, right? So this experiences some B naught field, right? And maybe I go here and it experiences B naught plus, some delta B. So basically, you could just assume that whatever the average delta B is here, and typically the gradients are such that, a typical gradient might be, say, 4 Gauss per centimeter, right? So over like a millimeter, there's very little change in that field. I mean, remember, a Gauss is on the order of Earth's magnetic field. So we're talking about very small changes in the field as compared to this main field, which is, as you saw, I think, 60,000 times stronger at 3 Tesla, right? So you're talking about, even if you average over a small volume, it's basically the same number. Yeah. Question.
So the goal of this question, right, was to calculate like the change in that Larmor frequency. And so by calculating that and taking its inverse, we get the period at which it will be reintroduced at the same cycle at 1 centimeter, right?
Yeah, at the same sort of orientation.
Okay.
Yeah.
And then so like back to like that previous question where you have like B naught being experienced here and then B naught like plus delta B being experienced like over here, like the B naught plus delta B is experiencing like that difference in frequency, right? That frequency.
Yeah, the delta B creates the difference. So basically the delta F is just equal to gamma times delta B.
Okay.
Yeah, or 2 pi, gamma over 2 pi. Okay, question. Let's see. Why is the phase negative? Oh, because they're still, let's see, what was the question? What will the phases be? Okay. Oh yeah, so the question there was, so basically the way to think about it is the fastest spin made it all the way around, right? It went 2 pi, right? So if I go twice as slow, I'm only going to go pi, right? So pi and negative pi doesn't matter, right? But let's say I'm this spin here, which is only 1/4, has 1/4 of the frequency difference. So it's going to go 4 times as slow, but it's still faster than the spin at the isocenter. So instead of going around 2 pi, it only makes 1/4 of the way there, but it's faster, so it's still a negative angle. So that's minus pi over 2, right? Yeah. Okay. All right, so let's go on. So just a reminder, everything is going to be now in the rotating frame of reference. Erwin Hahn was a very famous physicist at UC Berkeley who died a couple years ago. He said that there's nothing that nuclear spins will not do for you as long as you treat them as human beings. Okay. And so typically this is like when we're talking about like if you sit in a room with like MR physicists or engineers, we're always like trying to imagine what the spins are doing, right? We're like, oh, it's going to do this, it's going to do that. Which way will it go? Like a lot of hand gestures and things like that. So basically, because we're trying to think about, these are really spins are actually in a way like perfect human beings in the sense they'll do exactly what you tell them to do. Okay. Whatever the field is, they will process at that field. Whatever the T1, whatever the local environment is, determines their T1 and T2. It's just you don't really know all those things. And so, and then also the other thing is when you're designing some new method, you don't know everything, you make wrong assumptions. And so you say, oh, I'm going to design this method that does this. You design it, you program the MRI scanner, you go to the scanner and like nothing works, right? It's not the spin's fault. It's just you made a mistake. It's like, oh, I thought the spins were going to do that. The spins did exactly what you told them to do. It's just you told them to do the wrong thing. Okay. So so that's one way of looking at spins. So this is an exercise pre-COVID. We used to do live, like with people becoming human spins, but now with Zoom and everything, we're going to do it. This is the post-COVID version of this exercise. Okay. So so if we were doing this the old-fashioned way, we would have 5 of you come up here and you would all point in the same direction. So that's called that theta equals 0. Okay. And then basically the next thing we would do is we would tell the spins to precess, assuming there's a B0 field going this way, right? And these are the spins going in theta direction. So in a uniform field, and if we say precessed, then they should all rotate clockwise at the same rate, right? So that's the experiment. Okay, so in the laboratory frame, they would all rotate clockwise, right? And then the next question, which is the one that typically at least one person won't do the right thing, is we'll say, okay, now imagine you're in the rotating frame. And I say precess. Okay, so what should the people do? They should do nothing, right? But typically 1 or 2 people will like start moving. And then they'll start moving and then they'll see the other people are moving and then they'll go back. Okay. So basically that's what the experiment would look like. And then the next thing we want to imagine is there's these 5 people and we put them in a gradient field where it's stronger on that side of the room versus this side of the room. Okay. So now the people on this side of the room are going to have a net clockwise rotation, right, at every step, right? And the people on this side of the room are going to have a net counterclockwise rotation. And the farther away they are from isocenter, the more rotation they're going to do at each step. So that's what we're going to show you in this graphic here. So here is after the first step, you can sort of see the person in the isocenter has the boring job of not doing anything. Okay, that person never changes their orientation. This person here has gone clockwise by 45 degrees, or I guess 90 degrees. This person has gone counterclockwise, right? This person here has gone all the way this way, and this person here has gone all the way that way. Okay, but you can't really tell because they've both gone plus or minus pi, right? But what you're seeing here is if I just look at this one increment of time, I start seeing, oh, this is an interesting pattern, right? It's sort of, you could almost start imagining like a sinusoid here, right? Right, this variation, right? And I go to the next step, and this person has gone yet another 90 degrees. This person has gone another 180 degrees, and so on and so forth. And you notice here, the pattern is different, right? So the question is, which of these has a higher spatial frequency in terms of variation? Does this have a higher spatial frequency or does this have a higher spatial frequency? Which would you say is varying more quickly? The third one, right? Because it's going forward, backward. So it's changing a full period. This is a period, right? Whereas this one, the period is twice as long. Okay. So if we're talking about where we are in frequency space, this would be at some lower frequency. So this has let's say the period, we'll call the total period, let's call this like W. Okay. So this has a frequency of 1 over W, right? Or let's call it F. Okay. And this has a frequency of 1 over 2W. Right. So we've gone from, and what about this frequency? What's this frequency? 0. Yeah. Because there's no variation. So that's what 0 frequency means. No variation. Okay. So we've gone from 0 to 1 over 2W to 1 over W. Now here we keep going. And what's the period of this? And what's the frequency of this? 1 over 2W. Okay, cool. So we have 2 of these, right? So what's different about rows 2 and 4? Or so, yeah, 1, 2, 3, 4. Yeah, 1, 2, 3, 4. So rows 2 and 4 have the same frequency. Yeah, go ahead.
The phase,
Yeah, what do you mean by the phase?
row 4 is 180 degrees.
Yeah, if you look at sort of they have the same frequency, but this person is facing forward. This person's facing forward, right? This person's facing backwards, right? So what you're seeing is when you have a phasor, you can think of it can either sort of rotate clockwise through space or anti-clockwise through space. So that's what you're seeing. So that's what the definition of positive and negative frequencies are. They have the same spatial variation, but their orientation of variation differs, and that's what you're seeing. Okay. And then in this example, we go back to f equals 0 at the end. All right. So this is essentially what the MRI gradients are doing. They're allowing us to impose different spatial patterns in our spins. Okay. This is just another view of that from up top. And so what we want now is we not want to start thinking about how do we actually start tying this to the Fourier transform. Okay. So remember, this is the definition in 1D of the Fourier transform. I want my object and I want to multiply it by some phasor pattern, which has, in this case, at a given frequency, kx, and a given location x, okay? So at every location x, this is going to have some phase, right? Where the phase is basically minus 2 pi kxx, right? And so it's got some phase here. And so let's just look at an example of where, let's say kx equals 1, x equals 0. So if I'm at x equals 0, I'm going to have a phase of 0. If I go to x equals 1/4, now 2 pi kx is equal to pi over 2, and then the theta is minus that, so it's minus pi over 2. So that spin is there. X equals 1/2, the theta is pi, or negative pi, it's the same thing. And here I've gone all the way. So this spin has actually gone all the way this way, right? So this is also equal to minus 3 pi over 2. All right. So this is just saying that if I have something, if I have some kx value, then as I look along the x-axis, what this term is doing is just varying the phase. And so that's where we can go back to our simple example where we started off at kx equals 0, so everything is in phase. All the thetas are equal to 0, right? Now let's say kx equals 1/8 delta x. So this is 4 delta x. So this is half a period. And so you would imagine you only get half. This from here to here is only pi phase difference. And you can sort of see here, this is the isocenter. This one here has gone forward by 45 degrees, pi over 4, okay? Because if I take 2 pi 1/8 delta x, I multiply by delta x, right? I get, what do I get? Pi over 4, right? Okay. And it's a minus pi over 4 because it's going at a faster rate, right? And then here, if I go on to, whoops, 2/8 delta, so this, let me just write here, kx equals 2/8 delta x. Then you can sort of see here, I'm at a higher frequency, right? Because here, this is half a period here, and now this is 1 period. Okay. So as I go out to higher k values, I'm just going to shorter and shorter periods, right? So that's where we want to, so yeah, we'll start the discussion today. So what we're headed towards is we want to somehow implement this Fourier transform. And so we can see that, you know, with the gradients, we can sort of implement this spatial pattern, right? And the question is, can we implement this specific pattern of the phases? Obviously, the answer is yes, otherwise we wouldn't be talking about it, but that's the key, right? That the gradients actually allow us to implement this, okay? So we want to understand this a little more. And so what we're going to do now is we're going to review a little bit about Fourier transforms. Let's see. Trying to think. Okay, yeah. Let's review a little about Fourier transforms. So this is obviously covered in some of the supplementary materials, but we'll just do since we're sort of at the end of the time here, let's do a review of this. So remember, we have image space and then we have Fourier space or K space, and we will use Kx, Ky. Now the book uses U and V for Kx and Ky, but I don't know why they did that, because all MR people use Kx and Ky, so it's a weird choice. Okay. All right. So a couple things. The center of K-space is really important. It's just sort of the mean, or it's the average. It's the area under your function or the area under your image. So because the area is related to the mean, it's essentially the mean value of your image. Okay. So if you have a lot of tissue in there, you're going to have a large mean value, and then the center of K-space will be higher. The most important thing, though, is to think about plane waves, okay? And so, or sort of two-dimensional phasors, which not everyone's too comfortable thinking about it, but it's not, it's sort of straightforward. So let's go through it. That this 2D complex exponential just has a cosine and a sine term. And let's just look at the cosine term in terms of its variation. So the cosine 2 pi xx, if I had just that, then it would just be variations along the x direction with the period of 1 over kx, right? And similarly, if I just had a ky component, it would just be this variation. And then the key is if I have both kx and ky, now I'm going to have variation in both the x direction and the y direction. And then it turns out the period now has this sort of slightly more complicated relationship, but it's just a Pythagorean theorem relationship. So you can sort of remember it pretty easily. Okay. This just goes through the math behind how you would derive that. If I'm at some point in kx, ky, then the magnitude, sort of the overall frequency is this kx squared plus ky squared. And that 1 over that is where you get this period. Okay. So it's pretty simple. You just have to think about anywhere you are in K-space, that tells you the magnitude of that vector tells you the frequency you're at, okay, in terms of its magnitude. And then the relative combination of kx and ky tells you at what angle the variation is at, okay? So for example, if let's say I say in kx, ky space, I have some component here, then I can imagine drawing this vector out to here and that angle of theta, okay? That means in image space, x, y, at that same angle theta, I'm going to have variations. Okay, so anytime you look at something in K-space, if you want to know what its effect on the image is, you can just draw the perpendiculars to that vector, and that will tell you exactly what the angle of the variations is. All right. So here, just showing if I'm in this K-space, imagine I'm drawing here. The perpendicular is obviously this. And then if I go farther out in K-space, the spacing period just decreases. If I go along here, then the perpendiculars are this way. I go farther out, the spacing decreases. And if I go diagonally, then I imagine drawing a vector out this way. I draw the perpendiculars to it. I get that variation. Okay. Yes, question.
So these plane waves, these are like the direction in which like that wave would oscillate in K-space, or like.
Yeah, so that's a good question. So these lines I'm drawing are just sort of showing where the peaks of like the cosine would be.
Gotcha.
Yeah, there's not actually any propagation of the waves in this case, although if you're doing E&M and stuff, then obviously that's the K vector and that's the direction of propagation. Okay. Right now, that's just a simplified view. And just to remind you, so the center, what you're showing here is the Fourier transform of this object. And we're going to build up this object slowly by incorporating more and more of the Fourier transform as we go on. And so you sort of see here, if all I have is center of K-space, I just really have a very low resolution view of my object, right? Because all I have is the low frequencies. And as I incorporate more and more, then the images, I start filling in the details, okay? So that's basically showing you sort of one way of looking at the difference, the sort of how the outer parts of K-space are the details, and the inner part is sort of the overall shape of the image, okay? So for example, here, whoops. I don't need much of K-space to tell that this is a human, right? Like around here, I'm pretty sure that's a human being, right? Here, like at this point, you don't know, right? So you don't need much of K-space, right? I mean, here you could probably guess it's a human, but it could be something else, right? Pretty much right there. It's like, oh, that's got to be a human being. Okay. So that's not much of K-space, right? But if you had something with your brain wrong with your brain, you wouldn't want the doctor to make a diagnosis on this image, right? You're not like, ah, yeah, that's good enough. Just, let's go ahead with the surgery. I sort of know where the tumor is. Okay. No, you would want them to keep scanning and get more and more K-space so they know exactly where the tumor is. Okay. So that's the trade-off we're going to be talking about is how much of K-space do we actually need to acquire? Right. And that's, whenever time you go and get an MRI scan, basically, the doctor will say, hey, I want an image. Typically, there's a set protocol, but that's based on, from their knowledge, what sort of resolution they want versus how much time it takes. And that's typically the trade-off. Question.
And K-space is the Fourier transform of your image.
Yeah. So we just, in MRI, we just call it K-space, but it is the Fourier space. Okay. So here's some examples where here's the object, here's the K-space, and here I've gotten rid of all the components out here, okay? And so remember, the components out there would be used to represent edges, like these sorts of edges, right? The ones going like vertical stripes, right? And so you can sort of see here, if you look at this one, this edge here is really well delineated. So the brainstem here, right? And even here, you can sort of see in the cerebellum, really nice delineation. Over here, the corpus callosum, very nice edges going this way. Okay, going left to right, all edges in all direction, really nice delineation, all right? Here, let's look at this image. See that edge here, which used to be nice and sharp? It's all blurred out now, right? Because I've lost a lot of the detail. Whereas this edge here is still pretty sharp. The edges, the horizontal edges are still pretty sharp. Okay. Yeah, and there's other examples in the supplementary lecture that you can look at. So here's some interesting things. So these are examples. These are just synthetic examples, but occasionally we do see these in MR, and these are what are called corduroy or zebra artifacts. Okay, so occasionally there will be some energy or some noise that gets into the system, either because there's a problem with the shielding of the room, or sometimes MR is super sensitive. So even if you have like two pieces of metal just like hitting each other really lightly, that can create enough RF energy to create a spike. And so basically, as we're going through K-space, sometimes a spike will occur in the K-space. And so imagine I'm going through K-space and all of a sudden I get a spike here. This is going to create this pattern in my object. Okay, so for example, here, and that corresponds with if I drew a line to that face, I'm just drawing those components. And similar here, if the spike occurred here, then you would get that. Okay, so once again, it's just that. Okay, so if you're ever, if you ever get an MRI and you do sort of see some stripy patterns, it just means that that's what happened. Okay. Okay, so just to remind you, so to keep things simple, we've thought about these stripy patterns, right? But now we want to sort of get a little more back to MR, which is each of these corresponds to like a phasor pattern. Okay, and so you can sort of think of these things are sort of, this is where you can sort of see this has this sort of periodicity to it along these diagonal lines. And so it's really the lines of constant brightness indicate where along this line, all the spins are in phase. Okay. And along this line, all the spins are in phase. Okay. And it's just showing, I think this is just from this article, I think that's in the module, just showing that, because there's a lot of sort of edges and things in our natural world, especially the human world, Fourier transform is still very useful. Obviously, there's other transforms like wavelet transform, but Fourier transform is very useful. So let me just do 2 more slides just to help you, because there will be a homework assignment on this. So just remind you, kx equals 0, ky equals 0 just means there's no variation in either the x or y direction. Here, if I have kx equals 0, this means there's no variation along the x direction in any row, but there is variation along the y direction. Okay, so that's what that looks like. And then let's look at this. So Here's an example of kx equals 0, ky equals 0. So you can sort of see everything is in line. Here is kx equals 0.25, ky equals 0.5. So let's see if that's correct. So this would mean this has a period of 4, right? And this would have a period equals 2, right? Because 1 over the frequency is the period. So in fact, if I go from here to here, that is a period of 4, okay? And if I go from here to here, that is a period of 2. So I know at least the frequencies are correct. But now let's look at this. This is exactly the same, except it's kx equals minus 0.25. Okay, so it has the same period of 4 here and the same period of 2 here. But what's the difference caused by this negative sign? Can you see what's the difference between these two images? Go ahead. Yeah, the orientation, right? This guy went this way, right? And this one went that way. Okay, so that's the difference between the positive and negative k-space values. Okay, so any questions? This will end the class material here. I'll say a few words about the course logistics, but before I do that, any questions on the content? Okay, so course logistics, I think, so yeah, everyone, I think almost everyone did the MRI pre-lecture quiz, so there will be another one, but you won't have to do that one until like 2 weeks, like Monday. So you can either do it now or later. I'll post it later today, and you can either do it now while it's fresh in your mind or do it later. It's up to you. But you have a long time to do that. There will be a homework posted either today or tomorrow. It's going to be a 2-week homework. So you'll see there's some really easy exercises to do. So that's more just, it's probably the equivalent of about 1.5 homework assignments, but some of, so that's just because you have projects we don't want to do next week. So it's just more schedule your time depending on, how you want to get it done. And then for projects, there was an announcement. There's a lot of information out there. The main takeaway is the live projects are actually live. They will be in this room, okay? But we will use Zoom. So when you get up to present to the podium, you will have your computer, you'll be logged into Zoom, and you'll just share your screen. Because my computer, I'll be sitting here. Unfortunately, Professor McVeigh is going to be out of town. So I'll be sitting here so we don't have to monkey with this, with different computers hooking up, okay? So if you're the first person group, try to arrive like 5 minutes early so we can sit up and get going. And even if you're the second or third group, just arrive early just in case the first group doesn't arrive. And in general, be ready to go at any point in time based on, if someone has a problem with their presentation. Oh, and the other thing is, for the people presenting live, we do ask that you submit your slides like half an hour before the class. And that's only just in case your computer crashes or something happens. At least I have a copy here. We can always just show it from my computer. All right, any questions on that? Yes. Oh yeah, but you don't have to submit the code till like the later deadline. The pre-submission of the slides before the live is just to help emergency cases. Okay. And that's not like, if you want to submit an updated version of that later, that's fine. Typically we only use the slides in the code when we're like, we didn't quite understand what you were doing during the presentation. Well, we can go back and look at your slides and your code. So those are really more for help us to, if we want to sort of say, well, so typically what happens, we'll look at the code, oh yeah, it looks like they understood what they're doing. And then that just helps us give you a better grade. All right. Okay, great. So see you guys all next time.